Good day, everybody. Thank you for joining us for our session today on building an open source IPS IDS service on AWS with SuriCata. I am Nick Coval. I am a GTM networking specialist with AWS focused on network security. Been with AWS for about a year now. Before that, I spent 20 years in the managed network services business. Also today, joining me for the presentation, my partner in crime, Adam. Adam, could you introduce yourself, please?
Yeah, sure. Thanks, Nick. Hey, everybody. Name's Adam Palmer. I'm a specialist network solution architect with AWS based out of the UK. I've been with Amazon for about 4 years and spent probably 15, 20 years in the IT space working around converged infrastructure.
Awesome. Thanks, Adam. I also forgot to mention I'm hailing from Pittsburgh, Pennsylvania in the US, coming to you live on tape today. All right, well, let's jump in. So today on our agenda, we're going to talk about SuriCata inspection use cases, the primary ones we see our customers using SuriCata on AWS. Talk through some of the network appliance challenges that are associated to using form factors that SuriCata comes in. And then we'll talk about an AWS service, Gateway Load Balancer, a native service that helps us overcome some of these challenges. We'll go through some of the top use cases and then explain to you how the service works kind of under the hood. And then we'll talk about our deep dive use case today about how to actually deploy SuriCata. We'll go through a how-to quick start guide and show you how we do that to deploy it inline using ECS on AWS. Then we'll do a demo and a Q&A. All right, well, let's jump in. So the two top use cases, as I just mentioned, out of band and inline. And so on the out of band side, what you're doing is you have traffic that's going between a source and a destination, and you want to tap that or copy that traffic and send it off to a set of SuriCata instances that are someplace else. And so this allows you to do out of band and passive monitoring, so like a passive IDS mode. Some of the use cases you could do this for is for security inspection, NDR, XDR type of use cases. Also just doing PCAPs. So if you need to do some sniffing in your AWS environment to do troubleshooting, you can easily tap into ENIs that are around your AWS environment and then mirror that traffic over to your SuriCata instances. The AWS solutions team has actually built a quick start guide to help you get up and running to build this solution in your AWS environment. And we have a link to that here. On the inline use case, this is what we're going to dive deep into today here with Adam. This is when we want to inspect traffic between a source and a destination. And primary reason you want to do this is because you want to enforce security policy. So this allows you to actually block traffic if the traffic is not compliant or goes against your security policy. So this allowed, in this use case, you want to insert your inspection kind of transparently into the network, send that over to the SuriCata fleet for your inspection, and then send it back to your destination. But in this case, the SuriCata instances are actually inline. They're in the data plane. All right, so this is what we're going to dive deep into today. So before we get into the use case, let's talk a little bit about the challenges that network appliances present in the cloud. So businesses and enterprises use appliances they depend on appliances to protect and inspect a lot of their critical traffic moving around their environments. We use these on-prem as well as in the cloud. And these are typically inserted transparently into traffic flows inside of our network environments to inspect and protect and monitor that traffic. Often in the cloud, it's easy to set up and deploy these instances right throughout our VPCs. The challenges come in to when we want to be able to manage and maintain them at scale, along with providing resiliency and availability that really scales with our needs elastically. But often the drivers for using these that customers are faced with is they have existing skill sets or investments with technologies, vendors, or partners that they use on-prem, and they want to leverage that in the cloud. It helps them accelerate migration, do things faster, and be more agile. And so this is where we're trying to, in a hybrid environment, use these same appliances both on-premise and in the cloud. So the native AWS service, Gateway Load Balancer, helps us address and overcome some of these challenges. So on the left, you see before Gateway Load Balancer, you often deploy your appliances in an active passive mode. And in this case, your traffic going from your source to your destination has to be routed. and rerouted through these instances. And often they're deployed in the same VPC where you have your source or destination traffic, so that it can actually inspect the traffic. And the challenge with that is it creates this single point of failure because you're always dependent on the active appliance to handle the inspection. And then if you have a failure on the active appliance, you have to build in automation and detection technologies so that you know when the active appliance fail over to the backup appliance. Sessions often have to be restarted, so you have a traffic disruption. It's also a little bit more complex to insert it into insert the appliances into the workflow or the flow of data. So that causes disruption when you're doing the design and implementation and deployment. And the passive appliances are often sitting idle. So you're paying for licensing for appliances that are just sitting there waiting to handle a backup failure scenario. And you also have the challenge of mixed security domains. So in the case where you're deploying your appliances in the same VPC as your application, you might have an overlap of administration domains where you have your application developers or your security teams trying to control resources within the same VPC. And so Gateway Load Balancer helps us address a lot of these deficiencies. So it allows you to build an elastic, scalable, horizontally scalable fleet of appliances, and then greatly increasing the fault tolerance and availability of that fleet, of the overall service. It allows you to be elastic, and then as you go active, you're able to achieve that elasticity. And then with the Gateway Load Balancer technology, it uses VPC endpoints to allow for transparent insertion. So it makes it easy to add these inspection technologies to your existing VPC environments. And then because you can actually locate your instances in a separate VPC, that allows you to have those separate administrative domains where you can separate your users and your application developers from your security and network operations and infrastructure and cloud ops teams. So what are some of the benefits customers typically get from this type of service? Well, reduced downtime, because you're able to eliminate the failures associated to the single point of failures associated to those active appliances that you have to wait for the passive failover to. Improved performance allows you to reduce those bottlenecks that are associated to those vertical scale limits, because now you can scale your throughput horizontally across a fleet of appliances. Also allows you to reduce latency. Accelerating your migrations to the cloud, it's easier and allows you to do this easier and faster because you can leverage the existing technologies, skill sets, and relationships and licensing you've already invested in on-premises today before actually moving to the cloud. And finally, you get to lower your costs because you think about all those passive appliances that you have sitting idle. If they're distributed around VPCs in your environment, that's a lot of passive appliances that go away when you move to an active fleet and then centralize your inspection use case. So the two top primary sections of use cases or categories of use cases that we have customers using Gateway Load Balancer are our partner solutions and then DIY, where they actually build solutions themselves. So on the partner side, we have a strong set of partners that have developed solutions that run on top of Gateway Load Balancer. The common use cases here are firewalls, IDS, IPS. These are for the inspect and protection use cases, enforcing security policies. And then you have a set of vendors and partners that provide solutions that get you visibility, observability, and analytics. And those are often used for more passive detection, the out-of-band use cases for getting intel and even capitalizing on some of that, using some of that intel to do some XDR, NDR enforcement. And then this is kind of home to what we're talking about today. In the DIY world, we have customers that are taking advantage of the opportunity to build custom appliances and custom logic on top of Gateway Load Balancer for functions that they have needs for that either vendors can't provide or partners can't provide, or when they have the staff to be able to build it and maintain it in-house and not have to depend on partner licensing or support models. And so this is where we see customers using Linux deployments to do this. And this is exactly where our SuriCata implementations come into play. So I'm going to hand it over to Adam, and he's going to help dive a little bit deeper into how Gateway Load Balancer works under the hood to help us enable these use cases with the DIY use case.
Thanks, Nick, for the wonderful introduction. And I'm going to pick up here and talk about this DIY modality that Nick was alluding to. If we move on to the next slide here, just a little bit about how Gateway Load Balancer works. So I've got my laser pointer up here, and if you're not too familiar with AWS, I'll just go over some of the primitives of what we got on the screen here. These are VPCs, so the virtual private clouds, and it's a kind of a logical, isolated piece of the AWS cloud where folks and customers can go in and build internet gateways and deploy Amazon EC2 instances and create route tables and subnets and that sort of thing. So these green boxes are VPCs. And what we have here is a source, as you can see up here, and it's trying to get out to the internet over here, right? This is an internet gateway, and that is a cloud there, a generic cloud. So it's trying to do something on the internet. Now, what Gateway Load Balancer enables is packet flow to be redirected to a special type of endpoint, what we call a Gateway Load Balancer endpoint. And it's a function of actually entering a route in a route table. So that route goes in a route table. It sends traffic through a Gateway Load Balancer endpoint to a Gateway Load Balancer. And that Gateway Load Balancer can exist inside an isolated appliance VPC controlled by another part of the business or a partner of some such description. And what that Gateway Load Balancer does, it wraps up that original packet from the client inside GENEVE. And it sends that to a chosen backend instance. And it does that based on flow hashing of the original packet. So it makes a decision based on the hash of that flow. It chooses an instance at the back end. And then for the lifetime of that flow and the return of that flow, it makes sure that that flow always goes through the same backend instance. Now, in order for this to happen, the instance itself, be it a partner device or something that you've rolled yourself, perhaps in a DIY modality, supports GENEVE encapsulation. So we can see here that the original packet ends up going to the internet and actually comes back from the internet, but it's actually transparently inspected through one of these devices down inside this appliance fleet. It's sent out to the internet, the return packet comes back, it goes back through a Gateway Load Balancer endpoint, back to the same device that inspected it the first time, and then sends it back to the source. So you can think of Gateway Load Balancer, it's a combination of a layer 3 and a layer 4 load balancer, and a Gateway Load Balancer endpoint is a route destination inside a subnet and a route table for a client. So the next few slides are titled In Line with Amazon Leadership Principles. And I thought it would be a fun way to kind of convey to you the way I was thinking and my colleague Jesper and Nick were thinking about sort of how we go about helping customers build for AWS and what our thought process is. And Learn and Be Curious is one of those leadership principles that is exactly as it sounds. It's about learning about something you might not know too much about, being curious about it and seeing what you can uncover. And that's exactly what happened. So with the advent of Gateway Load Balancer and the use cases that Nick was alluding to there, we had customers out there that wanted to build this themselves. And so it got me on a path to thinking, how can a customer go about engineering something in a DIY fashion for Gateway Load Balancer? And truth be told, being candid, when we launched AWS Network Firewall, which had integration through the work that we've done with the OISF for Suricata, it sparked a lot of interest with customers, colleagues alike, and myself about learning more about Suricata. It's a product that I was aware of, but being completely candid, I hadn't spent a lot of time looking at the details and the mechanics of how it worked. So that's something I wanted to go and learn and understand. And that was really sort of started at the time when AWS Network Firewall launched and Gateway Load Balancer launched around the same time. And so, this was really about how do we help customers, and colleagues, because our internal colleagues are customers as well, right? So what are the options that we can give to them? And I think I was probably asked, a dozen times, is this possible to do yourself? Do I have to use a partner device for this? And the answer to that is, well, no, as long as you meet the requirements for using GENEVE encapsulation, this is something you can roll yourself, right? You can build it yourself. And if we look down here at this commit that is in the raw Suricata code, this actually evidences this integration, if you like. The work that OISF did with AWS about bringing GENEVE encapsulation onto the platform meant that Suricata itself could understand GENEVE encapsulation. And so what this said to me was, of course, well, if Suricata can understand that, then there's no reason to go out looking for something else that can do this. If Suricata can understand this straight away, let's explore this path with Suricata. And so that's exactly what I did. And so that began with a POC, a proof of concept. Any good project starts there, trying to evidence some value. And this really is an excerpt, if you like, of an internal page that I put together for colleagues in the network TFC and colleagues alike out elsewhere in the business about how they could actually build this using EC2. And these are, ClickOps type operations, right? This is me putting build commands in there to pull code from source and compile it and get the binaries together and set up IP tables and that type of thing. And what it proved was that A, it was possible, and B, there was interest in sort of turning this into a factory process. And so that leads me neatly onto the next slide, which is invent and simplify, right? How do we take this from just a POC and make this, almost productizable? How do you wrap something around this that you can use elsewhere? And so myself and my colleague Jesper, who's going to be joining us for Q&A a bit later, went through this process of kind of trying to understand of how we would go about this. And if you think back to the previous slide where we were taking code and we were sort of rolling it into an image and then saving that inside an AMI, an Amazon the machine image, storing it in S3, there's a lot of ClickOps there. There's a lot of work. And so we wanted a process where we could kind of maybe take some of that heavy lifting away and automate some of that. We also were thinking about how we could make it portable. It's great running on AWS, but what if you wanted to take this outside of AWS? Would this be possible somewhere else? If it's just standard sort of GENEVE encapsulation, could you take this code and do this another way? And so that factored into our decision process as well. And the desire to use sort of DevOps or GitOps based approaches here, we wanted to get away from sort of third-party tools necessarily to sort of build pipelines. We wanted to use native tools, and we wanted to use Git as a source of truth here. Essentially, what we wanted to start with was almost a user story that says, if I commit X to this code repo, that is the solution I would like you to build. And we wanted it customizable and extensible as well, right? We wanted builders out there to be able to take the code and say, hey, this is cool, but I'm going to make this better. I'm going to fork this and I'm going to do something else with it. And so we went with an approach where we saved all our code in GitHub. And I'm going to illustrate the solution with some WYSI diagrams in a moment. And that builds out various componentry on AWS. But essentially, the inspection mechanism is going to be using containers. So we decided to use ECS and Docker. So how does it all come together? Well, it starts with GitHub in the AWS samples repo, where myself and the builder community can fork the code and they can contribute to it, that type of thing. And inside that code bundle is a load of logic, but also a CloudFormation template that a customer can invoke from their AWS platform, from their cloud, the console, or through the API, right? So there's no restriction there. And effectively what happens is that person or that operator would invoke that CloudFormation script, or that template rather. Now that builds out some componentry. It builds out a sort of a baseline code pipeline mechanism, where the code pipeline definition, it builds out code commit for storing code, a code build operation for compiling code and building containers, that type of thing, and a code deploy mechanism, which is in itself uses CloudFormation again. It also deploys a Lambda function, and that Lambda function we actually use to pull the code back in from GitHub into code commit, and then set a release trigger on the code pipeline. Now, what this step enables folks to do is actually take the raw code out of GitHub, save it in code commit in a private repo inside AWS, and then modify it. And the type of modifications you might make here are the SuriCata YAML file, for example, that defines the engine parameters. You might want to go in there and turn some logging on, or change the way in which it inspects certain protocols. So you can do all this before you actually build the solution. And when you're ready, and when you're happy with what you have, you can release the pipeline. And the pipeline then builds out your inspection or your appliance VPC, as we saw on the previous slide, and your ECS cluster and your gateway load balancer and its endpoints. So moving on. What does the service look like when it's provisioned? Okay, so here's our inspection VPC, and it's deployed across 3 availability zones. We define the cluster, and the cluster itself has an ECS service that's inside of it, which kind of defines the tasks and the parameters for the service that you're going to build inside that cluster. Now, the ECS service itself is linked through ECS application autoscaling to an autoscaling group. The autoscaling group defines the type of compute that's going to be used. And the ECS service through ECS application autoscaling says to the autoscaling group, hey, I need some more resource. before we had this, it would be up to an operator to kind of control the amount of compute and resource inside the cluster. But with this dynamic linking between ECS itself and autoscaling group using ECS application autoscaling, that enables the ECS service to actually command the control over that and say, hey, I need resource based on various metrics. So this is happening. So the cluster is spinning up. And the ECS service also defines tasks. Now, each task contains 2 containers, as we'll see in a moment. And those tasks get deployed one per node. So we're using a one-to-one mapping of containers to nodes because we actually need underlying access to the host here because we're doing some low-level networking-based stuff with IP tables. Now then, once that pipeline is ready to go, we saw before there was an activation or release trigger, wasn't there? So once that's done and been released, code commit or any updates to code commit trigger the pipeline. The pipeline is going to look at those and make a decision about what it needs to do. And it's going to trigger code build. Code build is going to look at the Docker files, the descriptor files for Docker, see if anything's changed, and it's going to hash them. It's going to look at the previous definition or the manifest, if you like, and it's going to understand whether it needs to refactor those containers and rebuild them. It's also going to push config and textual config files into S3, and the reason for that will become obvious in a moment. So the containers get built for the first run and any subsequent runs, and config files get pushed down to S3. Now, the types of things that go into S3 are the real cool stuff, like rule files, Lua scripts, those types of things. Those types of things that can control the way that SuriCata works. Fundamental changes to the engines through things like SuriCata.yaml, they actually cause the container to be rebuilt because they are fundamental to the actual container mechanics. But rule files themselves actually are very dynamic in this sense, and we use code build and the pipeline to push those out. Now, once they're pushed to S3, we have 2 containers that are running inside each host, and the rules fetcher container, as part of the ECS task, is responsible for checking S3 for updated rule files. And when those rule files are deployed, pulls them down, and it invokes them as part of the SuriCata update process into the engine. At this point, we have running SuriCata instances on our ECS hosts, and they are loaded into Gateway Load Balancer, ready for service. This next one is around invent and simplify again. And this is around baselining and scaling. So some of the things we learned along the way. In the parameters file here, you can see how we can specify some of the core things that sort of drive the way the solution is built out. So we can specify log retention, and this is quite dynamic. So if you update this template file, CloudFormation, the pipeline will rebuild your stack for you, and it'll update the engine parameters. You can also specify instance sizes here. And so if you want to scale up, perhaps you need more memory, more network, or more compute, and it's not a scale out problem. You can actually change the instance size and the parameters here. You can also specify, as you see in my later pointer, an API key for MaxMind. So if you're using GOIP-based rules, you can put your API key in here, and the service will actually download the database for you and make sure it's available to SuriCata to use. Also, if you're using open rule sets from proof points, ET open, that type of thing, you can just put a textual string in here separated by a comma of all the rule sets you want to download, and the rules fetcher container will pull them down and load them into the engine as well. And going back to my point about good scaling and baseline, what we would say is that it's good to start with an instance size that has a good network baseline. A lot of the instances on AWS, and we have a lot of them, they vary in the way they work, and you want to be thinking about an instance that has a good network baseline that perhaps not. Essentially, you don't want your baseline performance to be below the baseline of the instance. You don't want to be bursting. So it's worth some calculation ahead of time of how many instances you're going to have and what your traffic profiles are likely to be. The same can be said of CPU and memory as well. Burstable instances come with CPU credits. If you go for something from the C range or the M range, they tend to come with guaranteed CPU allocation as well. So some thought will be required around that. But again, you can change the parameters dynamically for the instance size. And how does it work from ECS application autoscaling? Well, you define your SuriCata scalable target parameter in here as part of CloudFormation, and you say the namespace that you'd like to scale, and you link it here through a resource ID. And we can see here that the CPU scaling policy that we've created here is linked back to this scalable target. We've got some scale in and scale out cooldown times. And we're also looking at this predefined metric value of the ECS service CPU utilization. Now, this one is built in, but you can build custom metrics too, if you so choose. So dive deep. These are some of the more interesting things that we discovered along the way. Certainly, as I said before, being very candid about my discovery of how SuriCon works and things. We ran into some roadblocks, and it was actually quite fun to discover the way it works in certain ways. So we thought we'd highlight a few of them for you here. When we were building this out, I think originally we were using Docker Hub, and we were doing lots of builds. And of course, we got throttled pretty quickly because we were using anonymous credentials, and we're using Amazon Linux 2 from the Docker Hub repo. Our builds failed, our pipeline failed, we didn't know what was happening. Actually, some dive deep into that, discovered that, of course, we knew this, but we'd overlooked it. Yeah, there's limits if you're not a full member of Docker Hub and you're using anonymous request, you get throttled on based on your API request. So we moved to ECR, public repo from Amazon, so Elastic Container Registry, and inside there we have Amazon Linux 2. So we ported to that. We also had another interesting issue halfway through where we had a good steady state operation. And really, this is, again, probably down to myself and Jesper, not being declarative in versions. There was a binary update overnight. I can't remember whether it was a SuriCata dependency or a Rust dependency, but we had an issue with builds. And it turned out that there was an issue with Rust. So we moved our Rust in terms of our dependencies in the build out. We moved to the Rust up method to do that, and that resolved our issues. Because, as Nick was saying earlier on, we're putting traffic through inline, it enables us to do things like PCAP dumps. So if all your traffic is coming through this inline inspection mechanism, it stands to reason that you can dump this out to file. And so in our early testing, we thought we'd have the code working properly, and we weren't getting any output logs. And so we started tuning the PCAP engine inside the SuriCata YAML file. And the way it was worded, it sounded like we could actually specify a value in kilobytes or megabytes. I forget the actual wording was inside that YAML file now. So we started playing around with really low numbers, and of course nothing worked. Turns out there's a minimum of 4 megabytes for PCAP output files. So that's something we ran into as well. But that taught us to go and read the source code, which we did, and then we realized the error of our ways there. As I said before, we contemplated the idea of using things like building a central web console and maybe having some web interface to do cluster-based management, but we didn't really want to have to be so opinionated about how folks want to do this. So what we thought was, instead, we'll use Git for everything, as I said before. So our rule files are actually stored in code commit. So dynamic rules go into code commit, and when you make a change, in Git, you make your code commit, your commit to the repo, the pipeline runs, code build pulls down the rules, and then puts them in S3, and then containers read them. So we're doing everything from Git, and we found that as quite a nice way to operate. In terms of all the rich logs that SuriCata provides, we've provided mechanisms here to expose all of them. So if you turn them on in the SuriCata YAML, they will be pushed into CloudWatch logs. So we've got an engine that does that, and it just essentially uses the CloudWatch logs agent. Two of my favorite features on this, I have to say, if I have to pick favorites, were GOIP and Lua functions. We've provided or we've made provision to actually include this in the code. And so, as you saw before in the parameter file, you can actually specify a license key from MaxMind. And when you do that, the service will actually pull down the database and store it for use. Also, the Lua function, we've exposed an image directory inside S3, and the rules fetcher container pulls down those Lua scripts and makes them available for your signatures that you're writing inside your rule files. So these two really cool features, which I'm going to talk about very briefly in the next couple of slides, we've made available in this solution as well. And the last one here is go to the zoo. Cognizant of writing public blogs and things that go out to public outreach, copyright over images. I found some wonderful images of meerkats, as it turns out. I had a really nice picture I wanted to use, but I didn't own the copyright for it. So I took my kids to the zoo, as you do. And we went to the zoo, and I took this picture myself. I don't have a name for him, but perhaps we can debate that. But yeah, so this is the meerkat that's featuring on all of this marketing information. In terms of outreach, yeah, so myself and Jesper put together a public blog. sharing the work that we've done here and hoping that it would encourage customers to come, go and try this and experiment a little bit with it. And it's been really well received. I think within a few days of the post going on LinkedIn, we had over 2,500 reads and a bunch of reshares, 7 or 8 reshares of the post. A lot of hits on our blog channel. This is slightly out of date data by a few days, and a fair bit of activity on GitHub as well. So really encouraging to see. But not stopping there. reInvent is our biggest customer conference of the year for AWS, and it's an area where we like to try and take cool and up and coming ideas for customers to experiment with. And so what myself and some colleagues have done is we've turned this into a workshop at reInvent this year in Las Vegas. The actual workshop ID is Net 301 if anybody's interested, or you can get out to Vegas in November. It's a 2-hour workshop. It's gamified. And what we've done is we've a very complex application that includes web applications that sit in public zones. And we've got something called ingress routing, where we're taking traffic from one zone and passing it through to another zone for a payment site. We've got VPN attachments and various other mechanisms in there. And what we've asked the contestants, I should say, or the attendees to do, is effectively keep production running. So they have to, we build out the SuriCata solution for them. They have to attach it, they have to set up all the routing, and then they have to configure rules. They have to keep production running at all times, but they gain points for compliance. So if they can meet the compliance checks, effectively they play the role of a security consultant who's come in to fix findings in a security report. And they gain points, and they can see their points live on a dashboard. So lots of fun, and there's some stickers at the end of it as well. But we hope through this that the folks that turn up get a good understanding for how to engineer these inline flows and use these open source tools to write these IPS rules and signatures to protect their flows. So some useful links for you here. On the left-hand side, if you want to dive a little bit deeper into sort of the marketing information about how we talk to partners about how they can bring their devices to AWS to use GWLB answer, that's the QR on the left. The QR in the middle is the blog that I just alluded to, and the code in the blog is the QR on the right-hand side. We're going to cut now to a short demo where I'll show the service in action, and then we'll be right back. So hey everyone, welcome to this short demo. I just wanted to walk you around what the solution looks like in the console and maybe show you some of the rules in action. So you know that we built a pipeline. And so here is that pipeline. This is what it looks like. We have our source stage here, which is connected to code commit, and that's where all the code goes. On commit to that code commit repo, that starts the pipeline. And we have 2 build stages here. We have our SuriCata container build process. We have our rules fetcher container build process, our copy to S3 process, which copies down all of the code inside code commit so that the rules fetcher container can read it for things like rules files. And then our code deploy stage is down the bottom. And this actually deploys CloudFormation templates that have been built by code build. So what does the source code look like here? If we go into the repo, it looks very much like this. Inside the root of the repo, you have your dynamic rules. And so this is a rule file, essentially. And if you wanted to write a rule to drop some traffic, alert on some traffic, this is exactly what you could do. So what we have here, we actually have, I hope it's not too small for you, maybe I'll blow it up a little bit. We've got 2 rules in here. One is blocking all traffic that matches a header using a Lua script. And the other is blocking a TLS communication that is going to Twitch TV. So someone is trying to browse that website. We're looking at the SNI header effectively, and then we're dropping that traffic. So let's see that in action. If we go to this client here and open through Session Manager, I'm getting a console connection to this client. And actually, just before I do that, let me just show you what this looks like. So we have our client VPC, as you know, before that was probably at the top of the diagram. This is our source. And it's going out to the internet, but we're routing it through a gateway load balancer endpoint through a SuriCata instance that has rules defined. And that all lives in the filter VPC. That's where that ECS structure is. So the client doesn't really know anything about this. It just knows it's going to the internet, but we are inspecting the traffic as it goes there. So we're connected to this instance. Let me just bring this back up. So let's generate some traffic. So if I try and curl that website, we can see, interestingly, that the TLS communication was broken, right? That handshake didn't complete. We could run it again. In fact, if we took off the verbose mode and the headers, it would just sit there. So there's no response whatsoever. That was for the S&I header. The other one was for headers. So let's try and send some headers in to a website. So here's one I completed earlier. Save me typing it out, stay that. What we're going to do is we're going to send in a header value of header val and a header value, if you like, of block this value. If you can keep with that, the header is header val and the value is block this value. We're going to send it to Twitch TV again, because why not? And we can see here that it's not completed, right? So that hasn't completed. It's actually been intercepted and stopped. So actually, we know that the rules are working. Let's go and have a look and prove that out. So if we go into our log groups here, we can see that we've got even fast, right? So if we go into our fast.log, we click on our instance. In fact, if we go in within the last 1 minute, we can see the two rules that caught that traffic. The first one was block access to Twitch TV. We've got our rule ID, and we can actually see the source of the traffic was our instance. And we can also see our header protection rule working here as well. Now, something I wanted to show you here, and this is really about the onward delivery train and the value of AWS with this service, is that because these are log files in CloudWatch, you can do some really clever things with them. So what I've done as part of this log group here, I've created what's called a metric filter. It's a very basic example, but this just shows you the type of thing that you can do. And this metric filter is actually looking for a textual string inside the log. When it gets that, it's generating an alarm, and that alarm is sending me an email, which I've just received. So I'm going to drag it onto the screen. And this email just came in because we actually blocked the traffic. So you can see here that this alarm has just come in 15:01 my time. We can see that the reason for state change was I set this very low. So it's one threshold every 10 or 30 seconds. And this is the type of thing that your onward service wrap could really start to use and think about in terms of governance. But it doesn't end there, because what you could actually do from this is you could do something far more powerful. And this is very, very useful, but you could actually create a subscription filter. So that subscription filter, you can then invoke a Lambda function or a Kinesis Firehose subscription. So again, you can take this payload and you can push it into another service to do something with it. And that's all based on matching a textual string that's coming out, if you like, from the logs inside the fast log or the Eve log, depending on whether you're setting it up for rule matches or for flows. So just to close this out, I just wanted to show an adjustment to the rules. So if we come into here and we edit this, this was our rule base. All I'm going to do is I'm going to comment these out. I'm going to put my name in there. We'll go with A and rule updates. We'll commit those changes, and then let's just see what the pipeline does. Right, so we've committed the changes. Let's go to the pipeline now. Do a little refresh here. Took a couple of seconds, but it's now in progress. So we can see the pipeline is running. It's gone down to the build stage. Now, it's going to know when it gets to the build stage that actually the containers don't need to be rebuilt because nothing's changed in terms of their makeup. But the action to copy to S3 will need to be done because the files change with the rules in. So if we just refresh here, in fact, we don't need to because the copy to S3 has happened. Now, what the rules fetcher container is going to do is every 10 seconds, it's going to check the hash of that file. And if it's changed, it's going to invoke the Suricata update process or the binary there to change the engine parameters. So with a fair wind, if we go back now to our Suricata, to our instance and try those commands again, they should pass. So the first one that we tried was Twitch TV. Oh, there we go. So there is the full return data now from that website. If we put the headers on and put in verbose, you can actually see now that the TLS communication is completing and the connection is there to that website. And just to close this out, let's do the other one as well. There we go. So we were able to send those header values and that header type, if you like, through to Twitch TV. It didn't know what to do with them, of course, but it allowed us to do that. And that's just an example of a very short example, if you like, of how this service can be used. To find out more information about how to use it and how to work with the rules, including the static rule configuration that we've got in there and dynamic rules, check out the blog. And by all means, reach out to me directly. Thanks very much.
Awesome. Thanks, Adam, for that demo showing everybody how it really works. And thank you all for spending your time with us today. We really appreciate you exploring the project that we built here. We really want to hear from you. So if you would love to hear how you're using this project in your environments, please feel free to reach out to us. Hit us up on LinkedIn. And for more details, dive deep into the blog. Thanks again. Adam?
Yeah, thanks, Nick. And on behalf of myself and Jesper, who's going to be joining us on the Q&A, thanks for the opportunity to come and speak to you today. It's been a lot of fun putting this together. I know that we've all learned and been curious and learned a lot, if you like, with this product. So it's been a lot of fun. Thanks again.